lot of reactions that involve the exchange of electrons during the chemical reaction process. So if I look at reacting sodium metal with chlorine gas, it's going to be a very exothermic reaction in which I form sodium chloride solid, right? That's going to involve the basically taking of an electron from the sodium by the chlorine, right? Because it's going to form this ionic compound. So there's lots and lots of things that involve electrons moving around from one molecule to another, and which totally makes sense when when I said that Gen Chem 1 is going to be all about the electron. So we're looking at electron transfer processes happen all the time. Okay? So the first thing we got to do is figure out what oxidation states are. So these are sometimes called oxidation numbers, and they're going to help us keep track of electrons in redox reactions. They're defined as imaginary charges that atoms would have if they shared electrons or divided equally between identical atoms bonded to one another. Oxidation states on ions are represented as either plus or minus some number. And then we got some rules. So these are the rules for oxidation state. An atom in an element is zero. So if element is zero, so sodium solid, oxygen gas, O3 gas, Hg liquid, mercury liquid, those are all going to be zero. If you've got a monatomic ion, it's going to be the same as its charge. So Na plus is going to be plus 1. Cl minus is going to be minus 1. O2 minus will be minus 2. Okay. Fluorine is always going to be minus 1. Right? Always, always. You're always going to have a fluorine is minus 1. So HF, fluorine is going to be minus 1, which means this H plus has got to be plus 1. In phosphorus trifluoride, my fluorines, I've got 3 minuses, 3 minus 1s, which means that this guy here on the phosphorus has to be a plus 3, and each of these guys is going to be minus 1. Oxygen is usually minus 2, with a couple of exceptions, peroxides, and then oxygen is going to be minus 1. So in H2O, oxygen is going to be minus 2. Each of the protons is going to be plus 1. In carbon dioxide, we've got 2 oxygens, so minus 2 and a minus 2, which means that this carbon is going to have an oxidation state of plus 4. Hydrogen is going to be plus 1 in its covalent compound. So water, HCl, ammonia, hydrogen is going to almost always be plus 1. You will sometimes occasionally see hydride, where it's going to be minus 1, but most of the time hydrogen is going to be plus 1. Okay? Sometimes it's easy to see when we're moving an electron around, like our sodium chloride, but not always. Sometimes the transfer of electrons may not be evident. So if we look at the combustion of methane, the oxidation state, we've got plus 1 on each of these hydrogens, which means that our carbon is going to be minus 4 as its oxidation state. Remember I said carbon was really flexible, right? A couple of chapters ago, it could go either way, right? Here in carbon dioxide, it's plus 4. Over here in methane, it's going to be minus 4. So our protons, our H's, are each going to have a plus 1 charge, which means our carbon has to have an oxidation state of minus 4. Our oxygen is starting off with an oxidation state of 0 because it's in its elemental state, right? Element. And our elements are going to be equal to 0. When we look at the reaction, now here this oxygen is going to be a minus 2. I've got 2 oxygens at minus 2 each, which means that my carbon has to be plus 4. Over here on the water, these guys are each going to be plus 1 for the hydrogen and minus 2 for the oxygen. Right? So my hydrogens are going to stay the same. No electrons got transferred around on our hydrogens, but my carbon has gone from an oxidation state of minus 4 to plus 4. And my oxygens have gone from 0 to minus 2s. Right, so my oxygens have changed oxidation state, and my carbons have changed oxidation state. Carbon undergoes a change in oxidation state from minus 4 to plus 4. Oxygen undergoes a change from an oxidation state of 0 to minus 2. So 0 in its elemental state to minus 2 in its state where it's interacting with the hydrogens and the carbons. All right? So the terms that we give are oxidation is representing an increase in the oxidation state, right, or a loss of electrons, and reduction is a decrease in the oxidation state or a gain of electrons. We got two good ways to remember that, right? First up is Leo says Ger. So lose electrons, oxidized. Gain electrons, reduced. So that's one. Leo says Ger. The other one is oil rig. Oxidation is losing, reduction is gaining. Right? And then you've got my way of remembering it, because I am not that smart. I'm going to look at my element here, right? My iron. If my oxidation number on my iron 3 plus is 3, right, and it's going to 2, number goes down. If number goes down, it is reduced, right? That is a reduction. And then opposite of that, if I know my number goes down is reduced, if my numbers are going up, it's got to be the opposite of that, oxidized, right? So this way I only have to remember one thing and not two things, right? Numbers go down, reduced. In the combustion of methane, our carbon in methane is oxidized and our oxygen is reduced. Right? Oxygen is the oxidizing agent. So oxygen, O2, is a good oxidizing agent. Right? That's a good oxidizer. Oxygen is a good oxidizer. So if you can remember that oxygen is a good oxidizer, stuff on the other end of the periodic table, like lithium or cesium, ought to be a good reducing agent. So the opposite of that says, lithium or cesium would be a good reducing agent. And you can keep track of what happens to the oxidation numbers. If you think oxygen is a good oxidizing agent, well, if I got my O2 gas reacting with something and forming like H2O, well, I went from a 0 to a -2, it's going to go down, right? And if it goes down, I had to do what with my electrons? And I've got to pick up some electrons. So, our oil rig is still going to work, right? It's being reduced. Reduction is gain. So which of the following are going to be oxidation reduction reactions? All right, so identify the oxidizing agent and the reducing agent. We got 3 reactions. We'll start with the first one, go on to the others. So what you want to do in the beginning is identify the oxidation states. All right, so you look for some nice easy ones, like this zinc solid that's in its elemental form, and that's a 0. Right? If I go over here on this hydrogen, that's a 0. This guy's going to be a plus on this hydrogen and a -1 on that chlorine, which means that when I come over here, I got a -1 on this chlorine, and our zinc is going to be a +2. Right? Looking at this hydrogen, right, this guy here is the one that was reduced. If I look at what's happening to the zinc, right, my zinc is going from a 0 to a 2+, that's going to be oxidized. Right? And again, if you can't remember, think about what happens to iron, right? If I have solid iron, iron solid, and I make it react with oxygen, right? It's oxidizing in air. I'm going to form Fe2O3. Right? This guy's got a charge on it, +3. And this guy's got a 0 on it. So oxidation means that your oxidation number goes up. Right? Reduction means your oxidation number goes down. Right? So which one is the oxidizing agent? It is the thing that gets reduced. Right? So let's look at this one with the chromium. Right, so in our chromium, we've got oxygen here. I've got 7 oxygens. Right, so we're going to set these guys up, and we're going to have to account for this -2 charge. So it's going to be 2 times X for our chromium plus 7 times -2, that's coming from our oxygen, Here's our 7, and our oxygen has a -2. And this is our 2 over here, right? And then we've got this -2 charge. So those together have to equal -2. So what number needs to go in here? Well, math that out real quick. Right? And we'll do 2 times, so we'll find it's 6. So 12 plus -14 is equal to -2. Right? So you're just going to try and solve for x in these. So our chromium is going to be 6. Our oxygen is going to be -2. Over here, our oxygen is going to be -2. And our hydrogen is going to be +1, right? And notice that the sum of these is going to be equal to whatever that charge state is. Right? Over here in our water, our oxygen will be -2, our hydrogens will be +1. Our oxygens in here will be -2, but looking at this chromate, let's do that in purple. We'll do that as X plus -2 is the charge on oxygen. And we've got 4 of them. And it's going to end up being equal to -2 overall. So we've got, so our x is going to be equal to +6. Looking at our copper chloride, example number 3. Chlorines are always going to be -1, which means that this copper has to be a +1. Over here, this copper, because each chlorine is -1, but we've got 2 of them, this copper is going to be 2+, and this copper over here is going to be 0 because it's in an elemental state. So if we're looking at what is getting oxidized, well, our copper is getting oxidized and it's getting reduced. This copper is getting oxidized, and then the other copper, one of these other 2 coppers, is getting reduced. It's going from +1 to 0. So that means when we're looking at the electrons that are transferring, they're transferring between one of the coppers to the other coppers. This whole idea of reduction and oxidation is obviously super important when you're dealing in real world with metals, right? So bridges rust. They start to fall apart because of the reaction of iron with oxygen to form iron oxide. You also want to make iron, or you want to refine a metal from its ore, right? So in metallurgy, the process of producing a metal from its ore always involves a redox process. In the metallurgy of galena, so lead sulfide, the principal lead-containing ore, the first step is the conversion of lead sulfide to its oxide. So we're going to take our lead sulfide, we're going to react it with oxygen to form 2 lead oxide and 2 SO2s. We then treat our oxide with carbon monoxide to produce the free metals. We end up with lead oxide and carbon monoxide to give us lead solid and carbon dioxide. For each reaction, we want to identify the atoms that are oxidized and reduced and specify the oxidizing and reducing agents. Right, so we have 2 steps in here. If you take analytical chemistry with me, when we do this, we'll talk about the actual reduction and production of iron from iron ore and going from iron oxide and reducing that with carbon that traditionally came from coke ovens. So you take some charcoal and you burn it anaerobically to get pure carbon or coke, and then you would use the carbon as the reducing agent. So assigning the oxidation states in the first reaction, our sulfur, same column as oxygen, it's going to be a -2, which means that our lead over here is going to be a +2. Our oxygen is in its elemental state, right? So it's going to be a 0. We look at the other side, we got lead oxide. These guys are going to be -2. Our lead is still going to be +2, but now our oxygen is going to be -2. We're going to move the sulfur around. So when it comes to things like this, the more electronegative guy is going to be the negative one, if it can be. All right, so that's why fluorine is never going to be anything other than a -1. Right, fluorine's not going to give up its electrons. Right here, you got the oxygen and you got the sulfur. Well, this oxygen's more electronegative. It's going to basically take some of it. It's like, okay, I'm going to steal some of those electrons from you there, Mr. Sulfur. So our sulfur is oxidized. It's going from -2 to 0, and it's going up. And so our oxygen is going to be reduced, right? Our oxygen is going from 0 to -2. So oxygen gets reduced, right? Red for reduced, and blue for oxidized. Our sulfur is the one that is getting oxidized. The reducing agent is going to be the lead sulfide. Okay. For the next part, we've got our lead oxide. Our oxygen is still going to be -2. Our lead is going to be +2, right? Just like we had before. And then we got carbon monoxide. Our oxygen will be -2, which means that our carbon is going to be +2. Our lead is going to go from +2 to lead elemental lead, which means that the lead, the number is going down. If the number is going down, it's getting reduced, it's getting smaller. So this is our reduction. And then if we look at what's happening with our oxygen, it's going from -2s. Right? So nothing's happening with our oxygens, but our carbon is going from +2 to +4. The number goes up. It's the opposite of getting reduced. So this guy's going to be our oxidation. Right? So what I would expect from you guys is to be able to identify the oxidation states on different elements inside a reaction, inside a molecule, and be able to tell me which one is being oxidized and which one is being reduced. So which one is the oxidizing agent and which one is the reducing agent.